First of all, I would like to thank all of you, since this is really an enjoyable, nice, interesting week. And today I hope that you, at least some of you, even enjoy it even more due to this very, very, very interesting correlated material class of tantalum, nickel, selenide. Sorry for the stupid title, which is now Materialistic Modeling of Tantalum Nickel Diselenide, or Selenide, which doesn't mean anything. In the meantime, so between sending this title and doing further work, we realized we should more concentrate on the order parameter, which is now the reason why I'm going to try to convince you that we now ended up in a nice definition of the microscopic order parameter, starting from first principles. And to do this, actually a bunch of people were necessary. So there's Giacomo Mazza, who's hopefully somewhere in the audience here, who did the mean field calculation, the many-body calculation. Then there's a lot of work done by Lucas and Simone in Hamburg on the ab initio side. And here from Flatiron, we got some help from Janet Facano. And of course, Angel, Andy, and Antoine are involved in all of the discussion and as the driving force. So to give you my motivation, so that you just saw that this is already quite a group effort, but my motivation is to get a really material, realistic understanding of the many-body effects of this material class. And maybe just not in the material class, but first in this specific material. And specifically, I would like to understand, and I guess most of my collaborators would share this idea, what happens when we change, for example, the number of layers in the material class, what happens when we put a substrate, which might have a momentum as well as a frequency dependence in it, or what happens when we put in a cavity. And this is indeed, from a modeling point of view and a first principle point of view, quite a hard endeavor, since we are talking about a large number of electrons and atoms in the unit cell, and it's a layered structure, which means in general we can expect rather strong and long-range Coulomb interaction due to weak screening is maybe too much to say, but at least less screening due to the effective two-dimensionality of the system, which also goes hand in hand with sizable electron-phonon interactions. And the approach we took is a combination of ab initio calculation with some sort of many-body solution, higher-level many-body solver. And therefore, we do it in a multi-step approach. We start with first principle calculation. I'm going to show you in the next slide. Then we do what we call downfolded. We downfolded to a minimal model, which gets more treatable and also more understandable than the spaghetti band structure we get from ab initio calculation. And this model now will then include electron-electron interaction, electron-phonon interaction at some point as well, and of course electronic and phononic dispersions. And then we have a minimal model, which is then solved in some sort of many-body solution or solver environment here in the form of hard purified. Good. So let's start with the ab initio band structure as we get it from DFT when we use the high temperature, meaning orthorhombic phase of this of our crystal. Meaning here you see our nickel chain surrounded by the tantalum, meaning this is one of the most important chains, and there's yet another chain in the minimal unit cell. And if we do a GGA, plain DFT calculation for that, we get the band structure shown here on the left. And what you see is that there's no gap formed. We have 4 to 6 bands somewhere crossing around the gamma point at the Fermi level, but also weak inter-chain. So from here to this chain, inter-chain dispersion. So there is some dispersion, but weak point. And what is now missing in these DFT calculations for sure is some sort of Coulomb interaction effect. So as I said, so in a two-dimensional layered material, you would always expect to have some sort of long-range Coulomb interaction, which might not be missing in DFT, but is definitely heavily approximated there.
Can I ask you a question? Sure. So if you include spin orbit, does the gap open?
I don't think so, but no. Let's talk about the gap opening stuff later on. So what happens with the how do we now try to get the long-range Coulomb interaction in there? And one standard ab initio approach would be to do so-called W calculation on top of that. But this is a quite heavy numerical task for all of these hundreds of bands we would need to take into account. Although I would like to add that we are not yet there, but I think Simone and Lukas from Hamburg are approaching these GW calculations and converged GW calculation every minute closer. Our approach, therefore, is to follow Tsujimoto and other co-workers who did already similar studies, and we use some sort of hybrid, actually more something which is called a meta-GGA calculation, which is, let's just say, a black box which effectively introduces long-range Coulomb physics in an approximate way, and as you will see in a second, also in a senseful way. Under the problem, or with the constraint that we now get some sort of a parameter, which is called C, which we need to fix. So this is we never gain without losing anything, and therefore here we lost our full first principle, and now we need to choose this parameter. And this parameter now can be seen as a parameter which effectively tunes the strongness of the Coulomb interaction which we introduce. And if we now increase, so here I already increased it from let's say C equal to 1 in a GGA calculation to C equal to 1.2, 1.4, 1.6, 1.7. You see it has indeed a drastic effect to the band structure. And first of all, I would like to pronounce that it has a senseful effect of the band structure in terms of band widening. So let's, for example, keep a track here on this band, just going up, and this band width indeed widens with this we are increasing Coulomb interaction, which is something we would expect. That we open the band gap is something I would not expect a priori, and therefore I just need to say this is something we see here. So now what can we do with this parameter? I wouldn't believe actually this number. This is a highly unconventional number, and this has not been used so far to describe something senseful, and therefore we go back to the standard value, which is somewhat self-consistently calculated in this approach, which gives us this band structure, which I will now use as a basis to the modeling. Yeah?
Are you doing this with an experimental structure, or?
This is the high temperature experimentally originated structure, meaning we relaxed it in our DFT calculation completely.
Okay, so van der Waals between the layers is not hard to capture?
I would say it doesn't matter much.
Okay.
Sorry,
Yes.
do you have your result for software component as well?
Unfortunately, not yet, but it's in the making. You got it?
No, we need to get it.
No, as I said, it's in the making. Lukas right now in Hamburg is doing these calculations. So unfortunately, we need to stick to the selenide, but I promise even the selenide on its own is already very, very interesting, and we got some new insights since. So what we did next is to analyze, also like Tsujimoto and co-workers, what the main orbital contributions are. And here I shows a projection of this ab initio band structure to the nickel dxy and the tantalum x squared y squared orbitals. And what you nicely now see is indeed this upper band is mostly of tantalum character, and this lower band is mostly of nickel character. And even more, and this is the important point for us, and this is what we really like to see, it's just a single orbital on each side. With these 6 orbitals, now we have 4 tantalum atoms in the unit cell, 2 nickel atoms in the unit cell, meaning 1 orbital per atom ends up with a 6 orbital model. And using now these initial, let's say, guesses for localized Wannier functions, which we then optimize to get a simplified band structure, indeed worked out extremely well. Meaning these red bands I show you here is the result of a tight binding calculation which we gained from optimized dxy orbitals localized on these orbitals. And the fact that it perfectly interpolates this actually not that low energy area, so this is plus minus nearly half an electron volts and even more around the Fermi level, tells us that this is indeed a very, very nice, good minimal choice for this low energy subspace. So what does it look like in more detail? So here I plot in a slightly different color code, sorry for that, the resulting Wannier functions. And you see already from the top view and the side view that these Wannier functions all have 4 legs, meaning we are indeed talking about some d-orbital-like characters or orbitals, where the tantalum orbitals have their blue or negative legs following the chain direction, and the red leg, the red one, is sticking out of the plane. Red is sticking out of the plane, blue is going in. On the nickel side, we also have a similar one, but now this is rotated by 45 degrees, pointing towards the selenium atoms. Yeah, but still a dxy orbital line. And by this minimization or optimization procedure of constructing these Wannier functions, now we effectively took the selenium parts, which are of course here in terms of p orbitals, also into account. So by rotating these orbitals, by reshaping them, we get this selenium contribution. This is also the reason why we can all describe the band structure here as well, since there is some severe or significant selenium contribution there as well. However, we can describe the whole band structure in the area of interest with these 6 orbitals. And this is now how we sketch it or write the cartoon. So this is this tantalum d orbital, which is slightly tilted in these chains, and this is now the nickel d orbital, which looks in this close view in one of these chains like that. Now we can analyze the hopping parameters. Since we have these Wannier functions, we can calculate the overlap matrix element of the Hamiltonian, giving us the hopping matrix element. And what you see is that the nickel intrachain is rather strong, long range, as we would have expected. The same, now symmetry is important, very, very important. We now apply these, this mirror symmetry over here. You see that I will need to flip plus and minus here, which gives me a minus sign. And this one will be mirrored to this position, also flipping plus and minus, meaning I will have another minus sign, ending up with the same sign in the hopping to the left and the right in the nickel chain. Tantalum chain looks very similar. We have stronger hopping, which is a result from the larger bandwidth, or which is resulting in a larger bandwidth of the tantalum band, or tantalum-like band, with also some sort of decaying process intrachain. And again, doing this mirror, I will get actually in this case no sign changes at all, meaning to the left and the right, it's the same. Now the important part is what we realized during this modulation is it's not just nickel-nickel and tantalum-tantalum contributions, it's also a hybridization. There's also a bare hybridization in the minimum model already without Coulomb interaction between the nickel orbital and the tantalum. It's not too big, but it's also not too small and present. And you see it also doesn't drop down that fast to with the distance. And now, most importantly, when we now do the mirror symmetry analysis, we see that we need to flip the nickel orbital, getting one minus sign, and doing the very same for the tantalum orbitals doesn't introduce any minus sign, meaning to the left we will have hopping with a different prefactor than to the right. However, on the very same amount, so the absolute values are the same. Then there's another very, very important symmetry, which is the mirror plane here along the nickel chain, which doesn't change anything, meaning to the top and to the below. Top and below values are the same, but left and right come with the chains in the prefactor here. Exactly. So there's a non-zero tantalum nickel hopping already in the bare situation with this inverted sign. Exactly. So this is the pure Wannier model, meaning just describing the bare dispersion without Coulomb interaction matrix elements, which gives us, so this is the red one simplified, and if I also now label the orbital characters of our simplified six-band model, you see that in red is the nickel contribution, blue tantalum contribution. It mixes up more or less everywhere. Except, this is interesting to note, except for the gamma point. Since at the gamma point, this term, so k is equal to 0, meaning this term drops out, and we just need to sum over all t values, meaning if I sum minus 36 with plus 36 and so on, these off-diagonal contribution will perfectly cancel out, leading us, or yielding a situation where we have at the gamma point a perfect pure tantalum state and a perfect tantalum state and a perfect pure nickel state with. But everywhere else in the Brion zone, these matrix elements hybridize. And indeed, it doesn't matter from which kind of DFT or first principle calculation we start from. So here's another example doing the very same modeling for larger C, opening the band gap, we still get this hybridization. Meaning this is an intrinsic observation, intrinsic property, which we should not neglect. Right. So next to the hopping matrix elements, we need to talk about the Coulomb matrix elements, which we can nowadays also calculate from these materialistic downfolding procedure. Meaning we can calculate, we now have our Vanni functions, our wave functions, so meaning we have a basis in which we can evaluate our Coulomb matrix elements, and we need to not forget about screening. Meaning we should not take just the bare matrix elements living in our 6-band model, but we should think about screening processes arising from all the bands we now neglected. And these are bands like, or processes coming from a band which is not part of the model anymore to a band which is not part of the band anymore, model anymore. Then we have this from non-model bands to model band, from a model band to a non-model band. And in principle, there would be also for the full screening model to model or model band to model band polarization, which we drop out here in order to not double count them when we do the many-body solver on top of this model. But this is, in the end, this is a technical detail for the theory colleagues in the audience. Nevertheless, we should do this. And if we do this, we get the Coulomb matrix elements on site on the order of 2.4 for the nickel atoms. On the tantalum, we have 2.1. And this is an important part, rather long-range ones. So you see, yes, it drops down with R, but rather slowly. This is quite interesting to realize. This is also the same for the tantalum intrachain. And of course, there's nickel to tantalum Coulomb matrix elements, which also drop down very slowly. Good. Meaning.
Can I ask, what does that make? Do you understand that?
I
mean, the semi-metal, so there's no screening, I understand. But 1 over R would tell me there should be more like a factor of 2 difference if I go 2 units, and it's much less than that, right?
This is, I'm totally with you. The understanding I have right now is it's something we saw before in other 2-dimensional materials. So 2-dimensional screening is indeed completely different than 3-dimensional screening. Also on the level of the or especially on the level of semiconductor screening, which is there. And furthermore, I need to say, let me converge these results a little bit more before I claim too much here. However, long-range Coulomb interaction matrix elements is something we will have for sure, even if we can after converging. 5 more minutes? That is perfect. Meaning now you got the idea of the model. With the long-range exchange contributions, and most importantly, as I said, now we have this hybridization between the chains. And this means for us that this classical Falikoff-Gimbel model, which introduces on the bare side just hoppings within, let's say, the valence band, which is the nickel band, and the conduction band, which is the tantalum band, this is not enough anymore, since there are hybridization processes missing in the bare model already. And this means that we will need to think, or we need to introduce a new order parameter. And this is the take-home message, how we do this. So by mirror symmetry, we can now understand that this average values, so the average values of this hybridization, of this hopping processes, this possibility, this matrix elements, has to be to the right and the left coming with a different negative sign. This means if I plot this quantity, this average quantities, even without the Coulomb interaction, I get for setting the nickel contribution to R equal to 0 to the first unit cell, a situation like this. And here you see there's always this sort of inversion symmetry point here. We're showing positive and negative values, which leads us to the new order parameter suggested by Giacomo, which is now the sum of this left and right hopping. Since if we just pair the left and right hopping, we will always end up in the bare model without Coulomb interaction with 0. You see, you can just by the eye add them together, phi will be 0 in the ordered phase. So let's test this in the situation when we introduce Coulomb interaction and the effects of exciton condensation, or at least electron-hole pairing. And to do this, we quickly minimalize our minimal model even more, meaning we just take very simplified hopping matrix elements, nearest neighbors, but with this minus sign in this hybridization into account, take sensible on-site Coulomb repulsion and this nearest neighbor Coulomb interaction and solve it in Hartree-Fock and calculate now this quantity which is called phi. And if we do so, we get this. Now you see this order parameter for a given set of hopping matrix elements, which are chosen in correspondence to the model I showed you before, as a function of the local Coulomb interaction and the nearest neighbor Coulomb interaction. And what you immediately see is that there are indeed three different regions. So there's this A region, where we get a band structure like this. So this is some sort of overlapping situation of our tantalum and nickel bands, hybridized and with a finite Fermi surface. But, and this is the important point, you see that these expectation values still have these inversion symmetry over here, meaning they perfectly cancel out each other again. Meaning this is not the situation where this mirror symmetry here is broken. The same holds for the C area, where phi is 0 as well, where we actually didn't change at all these expectation values in contrast to the Baire model. And indeed, we find also just a gap situation. But now in between, you immediately see this. So red, I show you these hopping in the let's say the lowest part of this model, and blue in the lower part, and you see whatever you do, you cannot cancel them out by each other, meaning phi stays non-zero, and we are indeed now in this interacting electron-hole coupled situation. And this situation, this is nice to note, even with this minimal model, simplified model, we find that our complicated evaluated Coulomb matrix elements gets us close, and as soon as this is at least what we expect from the full calculation, as soon as we do the full calculation, the red cross should be in this region. Good. It gets even more interesting when we do these line cuts. So now I show you phi as a function of v for a given u. So for example, we are here at u equal 2.5 or something like this, and follow as a function of v. We see for coming from below, it's 0, 0, 0. Then we have this steep increase, meaning there's the first order transition going to a continuous transition for larger and larger v's. Right, so this means we now found that purely electronically, without any coupling to the lattice, we get the symmetry breaking effects, which is realized by this situation, meaning these hopping matrix elements are on average not canceling out each other anymore. So this instability, this symmetry breaking is something which is there already on the pure electronic side. Now, I think I have 2 more minutes, 1 more minute. 1 more minute is perfect. We also had a first glimpse into the situation, what happens when to the lattice, meaning Lucas and Simone calculated the lattice structure from DFT for t equal to 0, which indeed shows us shows a distortion which looks like this. So here you see, this is what we exactly saw in Kaneko's very nice first work. You see that these tantalum positions move a bit, which breaks exactly the very same symmetry as we have seen it on the pure electronic side. And this is the reason why we can immediately say these are 2 symmetry breaking effects, the lattice and the electronic ones, doing the very same and coupled therefore linearly. In this calculation, it turns out that this monoclinic phase transition or structural transition comes with this beta, which is not 90 degree anymore, but 90.57. And if you compare this to this STM data, I think we will see today as well. It looks a little bit smaller, but this is something we should discuss in more detail. Interestingly, very interesting and important to note is that in the symmetry broken DFT structure, including some finite Coulomb interaction, we see that we also already opened the gap. So this is something which might be a hint towards the exact physics we are talking about. And I think this is what Andre meant. The the minimal band gap here is not at gamma, but from this point slightly right or slightly moved away from gamma and indirect, at least in this calculation. Good. So meaning, I hope that I convince you that we are now at a stage where we have a minimum materialistic model in which we understand all symmetries in a most satisfying, hopefully, way. We have this new order parameter, which is a result from this, which breaks this mirror symmetry as the lattice does. And I would say in general, but this is something we should also discuss together, this fits to most of the experimental data we have seen so far, and also theoretical ideas we have heard about so far. Meaning we have this flattening of the band, which we see in the electron as well as in the lattice situation. We have tantalum contribution in the conduction, in the valence as well as in the conduction band. And okay, in general, we have a different or not strongly dispersive band structure, perpendicular to the chains. Meaning this picture in general is valid, plus the new hybridization which should be there already in the minimal model, in the bare model. With that, I would like to thank you for your attention.
Okay. Questions, comments? Good.
So if you start from a two-band Hubbard model and then trying to map it to the Falico-Kimball model, which you have, some extended Falico-Kimball model which you have used, there is some constraint on the intraband and interband interaction. Have you checked that this constraint is for field?
Oh, that I know. Did you check this? No.
Okay.
Honestly, no, we cannot comment on that. No.
Dennis, perhaps you can elaborate a little bit on what you
I'm just saying, you write down two-band Hubbard model which has intraband and interband, intra and interband interactions. Then let's just do a simple mean field, and you ask yourself what is the ratio between the intraband and interband interaction, where I'm able to map to a spinless problem. And there is some ratio. Yeah, that's it. We worked it out in the appendix.
Well, this is not the same band. These are not the same atoms. It's a local U nearest neighbor.
So exactly, local U versus non-local U. Yeah. They have to have certain ratio.
It has to have. Okay, let's discuss this offline.
Okay, I can show you the calculation.
You know why the region of excitonic insulator is so narrow with the vertical cuts?
Giacomo, I think this is the question you should answer before I push it around here.
Why is it so narrow? If I do a vertical cut in V, or indeed almost less so in U, but still the range over which I get this is quite narrow. Is there any qualitative understanding of why?
Well, why it's so narrow, what I can say is that I can say why there is a first order phase transition which is making this region so narrow. So the fact that as the order parameter grows, as you decrease V, and then it reaches a maximum, there is the point at which the bands touches. Basically, there is a lifted transition there between a system without a Fermi surface to a system with a Fermi surface. So I think that there is this first order transition which is killing symmetry localities.
So maybe just a comment to put these things in perspective. So, I mean, from all this, I think what appears clearly is that the symmetry which is broken already at the purely electronic level is a discrete symmetry, right? So the high temperature phase, and I'd be interested to know if anybody in the audience disagrees with that. The high temperature phase does not support excitons. So to a certain extent, it's a misnomer to talk about exciton condensation, right? Well, breaking the discrete symmetry, the low temperature phase, as we've seen from the talks this morning, supports excitons beautifully. The symmetry which is broken is a discrete symmetry, which I think is now very clearly understood. And of course, the excitonic order parameter, which is a scalar, couples linearly to the phonon modes that were also somehow discussed this morning. In particular, the obvious shear mode, as was emphasized by Tetsuya's work long ago. And it's all a question now. I think the electronic energy scales are now better understood from this ab initio work. And the next step would be to understand the electron phonon scales more quantitatively to be able to understand the couple dynamics. So at least that's my view of where we stand. I don't know if anybody wants to comment.
Any comment? If not, we leave the comments for.
We can discuss
it a little bit later. If not, when I'm listening Malte again.